This video will review Pythagoras' theorem, finding the length of the hypotenuse, the length of the shorter side, and the converse of Pythagoras' theorem. So when we label our triangle, C is always the hypotenuse, and A and B are the shorter sides, and it does not matter which way around you label those. Pythagoras' theorem states that a squared plus b squared equals c squared, and there are plenty of proofs of that out there if you have a look for them on the internet. And then we substitute into this. A is 5, b is 11, c we don't know. Evaluate what we can, and then take the square root. Now, this is giving our answer as an exact value. You might also be asked to give it as an approximate value, which would require you to round, usually to 3 significant figures, which is 12.1. And we would use the approximately equal to symbol rather than the equal to symbol to indicate that we have rounded. Just a short note, at this point we technically are taking the square root, the positive and negative square root of 146. But of course, in Pythagoras, we're finding a length, and so it makes no sense to keep a negative solution in there. And we tend to automatically disregard that negative when we're working with Pythagoras' theorem. In this second example, C, the hypotenuse, opposite the right-angled triangle, is 18, and one of our shorter sides is the unknown this time. A squared plus b squared equals c squared. We do not know a, we do know b, and we do know c. Evaluating what we can, we get that a squared is equal to 275. We take the positive and negative square root, disregarding the negative length automatically, and there's our exact answer. Our approximate solution, rounded to 3 significant figures, would be 16.6. The converse of Pythagoras' theorem states that if a squared plus b squared equals c squared, then triangle ABC is right-angled. So in these examples, we do have to make an assumption that it is right-angled and that the longest side is going to be the hypotenuse. Remember, it's only called a hypotenuse if we're talking with a right-angled triangle. Shorter sides A and B. And then I want to work out each side of Pythagoras' theorem separately. A squared plus b squared is 2,809. And when I check c squared, that's the same. Therefore, triangle ABC is right-angled. Okay, and that is because a squared plus b squared is equal to c squared. Which is the right angle? It's this one here. It's always going to be the one formed by the two shorter sides. So we could say angle ABC equals 90 degrees. And that's why it's a right-angled triangle. Following on from that, we can also use this to determine if something is not a right-angled triangle. So here, where I check a squared plus b squared, shorter sides being a and b, potential hypotenuse being c, 1.4 squared plus 3.5 squared is equal to 14.21. C squared here is equal to 4 squared, which is 16. So a squared plus b squared does not equal c squared. Therefore, triangle ABC is not right-angled. But we can go further with that and determine what type of angle ABC is, and therefore what type of triangle. We can have a right-angled triangle, which was the first example, or we can have an acute triangle or an obtuse triangle. And this will be one of those two. Right? It could be acute, right, or obtuse. We've established it isn't right, so let's have a look at which one is acute or obtuse. And these are the rules that we would be looking at. With the first one here, it says that if c squared, this hypotenuse here, for a right-angled triangle is c squared, if that length is shorter than it should be for a right-angled triangle, then this angle here is acute, not right-angled. If c squared, so the hypotenuse, or longest side, is longer than it should be for the right-angled triangle, then this angle here is obtuse. In our case, c squared is greater than a squared plus b squared. Therefore, triangle ABC is an obtuse triangle, where angle ABC is greater than 90 degrees or obtuse.